3? The one that just got graded?
Yes.
The last question about optimizing the travel time between airports. Where we had to create a graph and then sort of run Dijkstra's algorithm on it. In the grading, you said that I needed to have a source node and a sink node.
Yes.
But it's not a flow problem. It's just a shortest path problem.
No, yeah, I know, but the problem is if you create a graph, you have multiple flights that the departure airport is A. You have multiple boarding lines. So if in this case, you have to run the Dijkstra algorithm multiple times. But if you have the source node, you just need to run the algorithm once.
But don't you start, isn't there one starting airport?
Yes, the starting airport is A. There are only one type.
Okay.
But there are multiple flights that departure airport is not A. So if in this case, you have to run the Dijkstra algorithm multiple times.
But
So if you have the source node, you just need to run the algorithm once.
Okay.
You see the difference.
I do understand. I think I might have to talk to you more about it later.
Oh, yeah,
because I think in my algorithm I handled that differently because I said that there's one sort of starting point in time and then like waiting at that airport for the next flight is an edge on the graph. And so you're that waiting an hour to get the next departure time.
Alright guys, let's start.
Yes, the intermediate later.
Okay, so today we'll continue linear programming. Okay, so I went back and looked at how much stuff I did last time and I was pretty surprised. So I thought I'll recap a few of those. Okay, so I didn't, so hopefully most of you followed most of the things, but we'll just recap it in a little more detail than we normally do. Okay, because I think some of these are pretty important concepts and these are the kind of things that once you know them very well, you kind of take it for granted, which is probably why I zipped through them. So yeah, let's quickly recap. Okay. So the last couple of lectures, basically what we were doing has been, you try to phrase problems as optimization. Okay. So we looked at various problems, like many of them combinatorial, right? Like flows or matchings and stuff. And we tried to phrase them as optimization problems, right? And this basically meant you try to minimize or maximize some function f of x subject to some constraints on x. And x's are your variables and they depend on the problem. And one very powerful thing we saw last time is this, I said it's not a formal statement, but it's more of a rule of thumb. It says that typically you can minimize convex functions over a convex set in polynomial time. So it's not a general statement, but it's often true. Okay, so if you want to minimize a convex function over a convex set, then you can do this in polynomial time. Okay, and the standard algorithm for this is what's called gradient descent. Okay, this is something we saw last time, and it's basically local search. Okay, so you start at some feasible point, and you try to make local improvements. And what we saw last time is that if you cannot make a local improvement, then you're actually at the optimum. Okay, so in some sense, so any local optimum is also a global optimum. Okay, so this is a powerful thing that's true for minimizing convex functions over convex sets. And local optimum, as we defined, is you have a point, and if you move away from that point along any direction, the value of the function only increases. Okay, so it's like locally a minimum. So, and for convex functions over convex domains, local minima are the same as global. Okay, and we saw a proof of this last time. Okay, and this is where we used convexity in this clever way. Okay, so this is a powerful notion. And just to recap, a convex function is basically a function that satisfies if if you look at 2 points x and y, and if you look at the f value over the average point, then it's smaller than or equal to the average of the f value. Okay, so that's what's called a convex function. And then we saw a specific example of this, okay, where all the functions are linear. Okay, so linear is a subset of convex, so this is actually a special case of what I said before. Okay, so you want to, let's say, maximize or minimize, doesn't matter, a linear function subject to some linear constraints. Okay, so this was some random example. And we saw last time that a feasible set for this looks like this. Okay, so yeah, so I just wanted to have a more precise figure. So here, for each constraint, so let's say I look for this constraint x1 plus x plus 2x2 less than or equal to 4. Okay. So here, the inequality, this inequality corresponds to this half space. Right? So this is what we said. Each constraint defines a half space, and like this constraint corresponds to that half space. So every point on this side satisfies that inequality. Okay. And similarly, you can draw this for all these things. And then you have x1 bigger than or equal to 0, which is this half space. Everything is like this. Oh no, sorry, everything like this, and so forth. Okay. And this, the gray area here is basically the set of points that satisfy everything. Okay, that satisfy all the constraints. So this is a two-dimensional example. We said that in higher dimensions, you have a very similar thing. Okay, so you have a linear function which is before we go ahead, I forgot to mention what the objective is, right? So the objective is again some linear function here, and it turns out for this space, this is the point that maximizes this objective. Okay? So you can also think of it as the most extreme point along this direction. Okay, so the coefficients of this are 1 and 1. So the most extreme point along this direction 1, 1. Okay, so that's the other way of thinking about an objective function. And in this case, the most extreme point turns out to be this one. And more generally speaking, you have linear constraints like this, which you can often write down as some A1 transpose times x less than or equal to B1, and so on. And so in multiple dimensions, a hyperplane looks like this. Okay, so this region is probably something that's defined by this hyperplane. So, and then you have multiple of these, maybe you have something else that defines this set and so on. And we said that if you have a bunch of hyperplanes, their intersection, we were calling it a polytope. Okay, so there's just a name. So it's just an intersection of half spaces. And the main point is it could be infinite. Okay. So any questions about half spaces and polytopes? So one analogy people usually give for thinking of half spaces is you have like a giant potato and you're just chopping off pieces of it. Okay, so that's another analogy people usually give for thinking about half spaces like this. Alright, so this is usually this is the standard, this is the most general form of what's called a linear program. Okay, so you have constraints like this and you want to minimize or maximize something. Okay, so this is again a bunch of constraints and this is the feasible set. Alright, so the main,
So if it is infinite, then I guess one of your vertexes that could be a solution might be at infinity.
Yes, so if it's infinite, then you might not have a solution, in the sense that your solution could be unbounded. Okay, so think of, let's say a very simple example. where you want to find some space. Okay, so suppose you want to maximize x1 plus x2 subject to just x1 bigger than or equal to 0 and x2 bigger than or equal to 0. So in this case your domain is infinite, right? So your domain is the whole positive quadrant is your feasible set. Okay, so that's the polytope that you have now. And in this polytope, if you try to maximize x1 plus x2, then there's no extreme points in that direction. Okay? So the optimum is infinity, basically. So the optimum could be unbounded. But so I have to maybe make this statement more formal. So here, what I should say is either the optimum is unbounded or the optimum is attained at a corner point. So any other questions? So this is the theorem we saw last time, which is that if you have if you have any linear program, then the optimum solution is always a corner point. And we saw that sometimes the optimum solution need not be unique, in which case you could have points in between, but there is always a corner point which attains the optimum. Okay. And unless the optimum is unbounded. So this is something we saw last time. Okay, so there are many ways of proving this, but I think we intuitively saw a proof. We didn't see a formal proof. And we also said that this, this gives you a natural idea to solve this linear programs, right? So you know that you have a polytope, and you know that that the optimum is only attained at some corner point. Okay? So suppose you check all the corner points, then you can solve this problem, right? So this is a reasonable algorithm for trying to solve this linear program. Okay? But what was the problem with this? Anybody remember?
Finding corner points is not easy.
That's one. So, but we said that any corner point is defined by equality, right? So it's defined by a bunch of half spaces being satisfied with equality. Yeah.
The intersection of all the corners, it could be an exponentially sized number of corner points.
Yeah, exactly. So this is what we said last time, that the number of corner points could be exponential, okay, and it often is. So you'll see some simple examples in your homeworks where number of corner points will be exponential. And yeah, this is actually extremely simple. Even if you just look at xi is bigger than or equal to 1, bigger than or equal to 0, xi less than or equal to 1. So this is just a cube in d dimensions, and a cube in d dimensions has 2 to the d corners, right? So it's a very simple example. Even in such cases, you have exponentially many corners. Okay. So this is pretty infeasible. But we said that there is this algorithm called the simplex algorithm, which I described. And so this algorithm basically works by exploring corner points in kind of a local search way. Okay, so we said that you start at some corner point and you just move to a neighboring one. Okay, and we didn't quite define how a neighboring corner point is defined, but there's a standard way of doing this. Okay, so you move to a neighboring one and you keep going as long as the objective increases. Okay, and we said that there are a bunch of problems with this. The first thing is, how do you find a starting vertex? And this is usually easy in practice. Okay. And there are also many possibilities to move, right? So there could be many directions in which your optimum increases. And there's no right answer to this. There are a whole bunch of ways. So these are what are called pivot rules. Okay, so, and there's a lot of experimental study about what pivot rules work better and so forth. And so as I said last time, so we don't know if these kind of algorithms can be made polynomial. Okay? But the reason I just mentioned it is because this is one of the very successful in practice algorithms. Okay? So this algorithm is really successful in practice. So has anyone here used one of these open source packages to solve linear programs? Okay. So if you do, then usually all these packages have simplex and they have a bunch of other methods. And for most linear programs you can think of, simplex actually works the best. So it's, yeah, so that's why it's surprisingly good in practice. Alright, and this is the rough idea of the simplex algorithm. And then we said that for a long time it wasn't known if linear programs could be solved efficiently. And there was this breakthrough result of Kachian, and he showed that basically any linear program can be solved in time polynomial in the size of the program. Okay? And the size basically means it's the amount of space required to write down the program. Okay? And this again the same as what we saw in knapsack linear programming and so on, in flows and so on. Okay, so like if you have n bits, you could write numbers as big as 2 to the n. Right? So all those caveats apply. And so actually the ellipsoid algorithm is even more powerful than this. So we won't go into this, but sometimes you can even solve linear programs with a small number of variables but exponentially many constraints. Okay? And in fact, so what is needed to solve these kind of linear programs is what's called a separation oracle. So you don't have to really know what it is, but basically what it says is, I mean, as long as you can tell if a point is in your polytope or not efficiently, then you can solve a linear program. Okay, so this is a rather surprising thing. So I won't go into this, but I will. Yeah. So I have a link to some lecture notes on the course web page, and he actually does a very good job explaining the ellipsoid algorithm. Okay, so if you guys are interested, definitely take a look. Okay, so, but at this point, I just want to say that linear programs can be solved in time polynomial. And sometimes you can even solve linear programs that have exponentially many constraints, as long as the number of variables is small. Alright, so what we're going to focus on today is something we started last time, which is how do you use linear programming for discrete problems? So as I stated it, linear programs are basically, you have some feasible space, and this is like a continuous space. You have a convex set, and you have some linear function, and you maximize it, you get some point, right? You get some vertex of this polytope. But this is all a very continuous process if you think about it, right? There's no. So suppose you have a problem, a graph problem, like minimum spanning tree. There, what you want to do is find a collection of edges that form a spanning tree. It's not naturally a continuous optimization problem. Okay, so let's see some example. Okay, so I guess we saw this last time. So suppose you take max weight matching. Okay, or maybe for now, let's even take independent set. Right, this is even easier. So in max independent set, so here you have variables for every vertex, so you have a graph, and you have a bunch of edges, bunch of vertices. And the way we formulated it as an optimization problem is you have variables xu for every vertex that are supposed to be in 0, 1. Okay, each variable is supposed to be 0 or 1. And for all edges uv smaller than or equal to 1. So do you guys remember what the intuition was for this constraint? Why was this a valid constraint to put? Sorry?
Because this means that even we are not connected.
No, so I said for edges u and v, things that have an edge, I'm imposing this constraint xu plus xv smaller than or equal to 1. Okay. And the question is, why is this a feasible constraint?
Because otherwise they won't be independent.
Yeah, so basically the problem of independent set basically says find a collection of vertices such that there's no edge between them, right? So and xu equals 1 means that it's in the independent set. That's how we are capturing this problem. And so if xu and xv are both 1, that's the only case in which this can be bigger than 1. And in this case, you have an edge between vertices that were picked, okay, and that means it's not an independent set. Okay, so that's why this is a feasible constraint to add. And we said you can write it as a maximization problem, and then you can say maximize sum over u xu. This basically says pick as many vertices as possible. So this is how you can capture independent set. But this is not a linear program. So why is this not a linear program?
Set is not convex.
Which set? Yeah, which set?
0.
Yeah, so what we said is that linear programs must just have linear constraints, right? Like linear inequalities. Like if I had xi bigger than or equal to 0, this is a linear constraint. And if I had xi less than or equal to 1, this is also a linear constraint. But this allows you to pick any value between 0 and 1, right? So xu is allowed to be anything between 0 and 1. And this is a convex set, right? So basically you can't have a constraint like this in a linear program. A constraint like xu is either 0 or 1. Okay, so you can only, yeah.
So, are you saying that xu belongs to 0, 1 is not convex? Is that the argument?
Yes, because
But it's, I mean, you're defining your space is defined as discrete, right, not continuous. If your space was defined as continuous, then 0, 1 would not be.
right, but linear programs assume a continuous space.
Okay.
So everything works only, like convexity and everything are defined in a continuous space. Okay, so that's the reason. Okay, so it's a good point. So your space should be defined as a continuous space. Okay, so that's when you can use these kind of linear programming techniques. So one thing you can say is, okay, so I have these constraints and these are not convex, right? But then you could say, okay, let me just forget about the integrality part. So let me just forget about the fact that they have to be either 0 or 1. And then I just replace this constraint, xi belongs to 0, 1, with just 0 less than or equal to x less than or equal to 1. Okay? So I'm artificially making this convex. Okay, so in some sense. Okay, so replace this constraint with 0 less than or equal to xu less than or equal to 1. So is it clear what we are doing? So this process is usually called relaxing the constraint. So earlier you have this strong constraint that xi is either 0 or 1. Okay. Now you are relaxing this constraint a little bit to say that, oh, okay, you can be anything between 0 and 1. Okay, so it's so this is what's called relaxing this integrality constraint. And so the kind of questions we'll be asking today are: suppose you solve relaxed versions of these kind of optimization problems where you have xu belonging to 0, 1. Can you get any useful solution out of it? Okay, so that's what we'll see today. Okay, so that's the general theme, and it turns out, so we'll see two examples. So we'll see how in this case it's actually useful, in these cases it's not so useful. Okay, so we not get there first. So I'll start with one simple example in which we are extremely lucky. Okay, so in which it turns out replacing the 0, 1 constraint with 0 less than xi less than or equal to 1 doesn't really matter. Okay, so this is this weighted bipartite matching. I think I just started describing this last class and we ran out of time. So the problem here is what you guys have seen a bunch of times by now. So you have a bipartite graph, you have two sides, and you have weighted edges. Every edge E has some weight WE. Has weight WE. And what is the problem? You want to pick a collection of edges such that every vertex on the left has at most one edge incident to it. Right? So that's how a matching is defined. And same is true for the right side. And you want to maximize the sum of the weights of the edges you pick. Okay, so this is the objective. And initially think of xe as being either 0 or 1. Then this, along with the constraint that for every vertex u, so for every u over here, you've got to pick at most one edge that goes out of u. Right? So this is how matching is defined. Okay, so like if I take this u, then of these two edges only one can be picked. And the same will be true of some vertex u here. Of these three edges, only one guy can be picked. Okay, so is this clear? This optimization formulation for matching. So questions about this? Suppose you still have this constraint. Okay, for a moment, assume you have this constraint. Is it clear that this exactly captures matching?
So is that just to match each node to exactly one other node?
Yes. So basically you want to think of a matching as a collection of edges. That is what this guy is matched to. And you want to minimize, and you want to make sure that every vertex has only one edge out of it that's picked, or at most one edge. There could be some unmatched vertices for which this sum would actually be 0. But it doesn't matter.
And it's for both sides of the...
It is for both sides, that's important, because otherwise you could have two vertices being matched to the same thing on the right. Okay, so this is, so if you think about it, this captures matching in an exact way. And now you could do this relaxation that I said, right? So now you have this constraint xe belonging to 0, 1. You could say, I'm going to forget about this constraint, and I'm just going to replace it with 0 smaller than or equal to xe less than or equal to 1. Okay, so instead of xe taking values either 0 or 1, you're going to say, okay, you're allowed to take any value. And suppose I solve this optimization problem. Okay. Now, in principle, what is like a bad case to happen? Suppose I solve this, now this becomes a linear program, right? Because this is a linear function. So Actually, how many variables are there in this linear program? Just to make sure all of you are. Oh, in this example, okay, there's a little bit more than 8. It's 10, I guess. Yeah, it's exactly the number of edges in this graph. For every edge, you have this variable xc, right? So this is the number of constraints, the number of variables. This is the number of edges and number of constraints. How many constraints are there in terms of number of edges, nodes? Yeah, you have you have one constraint here per vertex, right? So you're saying that every vertex has this. You have this additional thing that each edge is less than or equal to 1. So you have number of vertices, which is this, plus 2 times number of edges. Okay, because for every x you have either 0, bigger than or equal to 0 and less than or equal to 1. Okay, so this is the number of constraints. And now this is just a linear program, right? So these are just a bunch of hyperplanes and you want to maximize this objective function. Now suppose you solve this problem, okay, so suppose you solve this, then how could an optimal solution look like? So, right, so this is some polytope that you get, right, and it's bounded. So why is this polytope bounded? Why is it not infinite?
Because you have more constraints than variables.
Sure, but boundedness doesn't quite have to do with that. By bounded, I just mean the feasible space is not an infinite sized set. Okay. I mean, it's infinite in terms of it's a continuous thing, so it's infinite. But what I mean is in terms of, let's say, the volume of this space. Yeah, it's bounded on both sides, so it's a bounded set, right? So what you have is in fact a subset of this cube. Right, so you have the e-dimensional cube, you have this m-dimensional cube, and what you have is like a subset of this. Right, so you have something that looks like this. Right. So okay, so let's say this is your objective, and now you maximize it and you find something. Right, so you found some point. Now the question we want to ask is, can I get a matching solution from this vertex? So is the point clear? So I have some vertex of this polytope which I get. Okay, this is what my, let's say, this is what ellipsoid or simplex algorithm gives. Now, what do you see could be a problem? So suppose this solution basically was it was something like 1, 1, 0, 0, 1, something. Okay, so suppose it only had 0, 1 coordinates. Then are you done?
If you have only 0, 1 coordinates, it means a matching solution is possible.
Yeah, exactly. So basically, if you had a 0, 1 solution, okay, so if you were lucky and you solved this maximization problem, and it turned out to just have 0, 1 coordinates, then you're in good shape because you actually wanted to solve a 0, 1 maximization, but you relaxed it and you solved this problem, but somehow you still got a 0, 1 solution. So what you have is still optimal even for the original problem that you wanted to solve. So in that sense, if you get a 0, 1 solution, then you are in good shape. Okay. So the problem could be that you have a solution that's not 0, 1. Okay, so for instance, like you could have a solution in which, this is what we saw last time, so you could have xe equals half for all edges like this. Okay. And maybe you have 1 over here. So this is a feasible solution, right? So for all 4 of those edges, you could have xe equals half. And this satisfies all the constraints, because if you look at this vertex, the total sum of the edges that's going out, sum of the x's for the edges that's going out is half plus half, which is at most 1. Same is true for this guy, right, for everybody. Okay, so this is something you can verify. But you know, this is not a very useful matching. Okay, so yeah, so this is usually the problem. Okay, so this is usually the problem when it comes to using linear programs for solving discrete problems. Okay, so you end up with vertices that could be non-integral. But it turns out that in the case of bipartite matching, we are actually very lucky. Okay, so it turns out that for this bipartite matching polytope, so this is what it's called. So you have some bipartite graph and you have this set of constraints. Turns out that all the corners of this polytope are actually integral points. Okay, so this is a non-trivial theorem and I won't prove it, but this is true. Okay. This turns out to be all 0, 1 values. Okay. And there are some problems for which this happens. Okay. That you just remove the integral constraints and you consider this polytope, and somehow it turns out that all the corners of this polytope are integral. And this is something which is special for bipartite matching. So in fact, in your homework you will see that even for general matching, it's not true. Okay, so you could have a matching in a non-bipartite graph. So there also, if you have this xe belongs to 0, 1, then this kind of a linear program suffices. But once you replace those, once you relax it, which means you replace those constraints with these, then there could be corner points that are not integral. But for bipartite matching, the very nice thing is that this doesn't happen. And what this means is that you can solve bipartite matching just by using linear program. Right? Because you can just write this linear programming relaxation. You know that any optimum solution is going to be a corner point. And this theorem tells us that every corner point is an integer point. Therefore, it has to be the right solution. Okay, so any questions on this? Yeah.
So what if you deliver a point that is maximum but not like that will still happen?
No, that's the point, right? So in any linear program, the optimum point, like a maximum or a minimum of any linear function, is always happens at a corner point.
Yeah, but it's not necessarily in this case, right? For example, consider the case in which the same example that I've given in the diagram, say all the edges are equally weighted.
Right. Then this is as good as another integer solution.
Yeah, but then you'll have to make some changes on it, right?
No, if you do a simplex,
So,
then you'll get.
yeah, exactly. So if you do any kind of so it depends on your LP solver, that's correct. So you could have, your solver could tell you that this is the optimal solution, this all half plus this one is an optimal solution. That's fine, but this won't be a vertex of this polytope. Okay. And furthermore, there will be a vertex where the value is at least as good as this. Okay. So this is what the previous theorem said, right? So what it said was, if you try to maximize a linear function over some bunch of linear constraints, there is always a corner point which attains a value that's as good as the minimum. So, I mean, in some sense you can assume that the minimum is a corner point. You could have ties like this where you have, and the reason this case it turns out to happen is that, so it's one of these cases where imagine you're trying to find a maximum point along a certain direction, okay, and you have two corner points that are at the same height, okay, then even the average point of these two, any weighted average of these two, has the same value for the height. Right? So this is what's going on in that example that you gave. Okay? So in this case, you might end up finding this. You might be afraid that you will find something like this, but as long as you only find corner points, like let's say you use the simplex algorithm, then you will never find a point like this. Okay? So you'll either find this or this, and these are always integer. Okay? So Yeah, so, but that's a valid concern. Okay, so that's, okay. So is this point clear? That not all optimum points could be corner, but there is always a corner point that's an optimum. Okay, so that's something to keep in mind. Right, any other questions? Okay, so this is fine. So this is true for certain problems, as I said. So this is true for bipartite matching. But now you could ask, what if corners aren't integral, right? What if not all corners are integral? Okay, so you have some polytope, maybe a few of the corners are integral, but there's also some non-integral corners. Okay, so maybe all half is something that's there. And now if you try to maximize along this direction, you will find this point. So how would you deal with this, right? So this is the standard problem we face when you try to solve discrete problems via linear programs. And the way we deal with this is this procedure is what we call rounding. This idea called rounding. When you say that, okay, so the linear program is not useful per se as such, right? Because it gives a solution that's it gives a continuous solution. What I want is a 0, 1. But the point is, maybe it still gives you some indication about a good integer solution. Okay, so that's the idea behind rounding. So if you knew that, let's say the optimum to this had 0.99 and then 0.01 and something like this, if you had weights like this, then you would guess that, okay, maybe setting that to 1, setting this to 0 won't affect my objective function so much. Right? So that's the idea behind this rounding. Okay, so it's this general process of convert a fractional solution to a 0, 1. So this kind of thing is called rounding. And how you do it is an art. Okay? In some sense, it depends on the problem. And so this is what you want to do. And the goal is to make sure that the objective is not too different. Objective value doesn't change too much. So you want to convert a fractional solution into a feasible 0, 1 solution. Okay, so into a feasible 0, 1 solution. Feasible in the sense that it satisfies it is still within the polytope, right? And you want to make sure the objective value doesn't change too. Okay, so we'll see an example in a second if this is too abstract, but it's a general idea clear. Yeah, do you have a question?
No, I think I'm okay.
Yeah, maybe we'll see an example. Yeah.
Does it always have to be 0, 1 that you're going for, or could it be any integral?
It could be any integral, but for most useful problems, you would just want 0, 1. So, I don't know of good examples where you would want integral but not 0, 1. Okay, so there are few what I call lattice problems where this sort of thing might be necessary, but for most problems we'll see it will be 0, 1. Okay, so we'll see an example of this, but abstractly this is what we want to do. Okay, so you have some problem in which you have these xe belong to 0, 1, some kind of discrete constraints, And what we do is you relax it and then you solve actually a linear program that you solve in a continuous space. And now you find a corner point, and this doesn't satisfy these integral constraints that you want, that x is 0, 1. And now you try to convert this into a feasible 0, 1 solution. Okay. The hope is that you don't lose too much in the objective value in this process. So this is what's called rounding. And rounding turns out to be a very powerful way to obtain approximation algorithms. Okay. And so this is we've seen examples of approximation before, but let me formally just state it again. So you have an optimization problem let's call this P, and let's suppose it's a maximization problem. Now, an alpha approximation for this, alpha approximation algorithm for P. Okay. So it's an efficient algorithm that for any instance I of P returns a solution the optimum solution for I. So what this says is, so suppose you have a maximization problem, right? So think of independent set. Okay, so usually these things are NP-hard problems, right? So if you have, let's say, independent set, and an alpha approximation algorithm for this independent set, so this is a polynomial time algorithm. Okay, so this is an efficient algorithm, and it has this guarantee that on any instance, okay, the solution returned by this algorithm has a value, has an objective value that's at least an alpha fraction of the true optimum on that instance. Okay, so that's why it's opt of I. So we've seen examples of this before, right? So we said that I think we saw a certain scheduling problem in which you wanted to in which we said a local search algorithm achieves this kind of a guarantee. Okay. And in your homework you also saw this matching problem for which you said if you do a local search you end up at a solution where it's at least half the optimum or something like this. Right? So this is formally called an approximation algorithm. And it turns out these kind of things are very useful because you might have some NP-hard optimization problem and you can't solve it exactly, but maybe if you have a good enough approximation algorithm, you're happy. Okay, so this is the reason people study approximation. And this is the formal definition. Okay. So any questions about the definition? So you guys have all seen examples of this and we will see a couple more today, but this is a formal definition. Okay. And similarly for a minimization problem, you can define the same thing, and there you have to say that your answer is not much more than the opt of I. Okay. Suppose your goal is to minimize. Okay, so you want to find the smallest possible value of some objective, and you can't quite find the smallest possible, but you find a solution that's not much more than the optimum. Okay, so this is like for some load balancing type problems. This is what we did. Okay, so this is for minimization. So let's see examples of this. And so what I want to illustrate today is how you can use linear programming to come up with approximation algorithm. Okay, so this is a very powerful paradigm, and it turns out this is one big application of linear programming. LP to give approximations. So the first kind of simple example that we'll see is vertex cover. So do you guys remember vertex cover?
Isn't it the smallest set of edges that covers every vertex?
You're almost right, it's the opposite. The smallest set of vertices that covers every edge. But, yeah, but it's good. That level of memory is what I was looking for. Okay, so this is a graph problem again. Okay, so you have a graph G, bunch of vertices, bunch of edges. And V and E. And the problem is find the smallest insides set of vertices, subset of vertices covers all the edges. And what do you mean by cover? So it just means that for every edge, at least one of these things must be picked. Okay. So, and we want the smallest such subset. This is a natural problem, right? So this is a lot of covering problems can be written as this. Alright. So suppose you were to write some kind of optimization formulation for this. So how would you write this?
For every edge, the sum of the vertices is equal to.
Yeah, so you could, it looks remarkably like the independent set problem, right? So what you'll say is, let's have variables xu for vertices, and these are supposed to be 0, 1. If it's 1, it means it's in the vertex cover, 0 if it's not. And we are saying every edge has to be covered, right? So which means that for every edge uv, you have xu plus xv is what?
Equal to 1.
It doesn't have to be equal. Well, as we said, you could have both. So in this case, I mean, that's also fine. So you just need bigger than or equal to 1. Okay. So it could be covered twice. It doesn't have to be covered exactly once. Okay, so you have this, and you have this. And what's the objective function?
Minimize the sum of the.
Yeah. So you want to minimize sum over u xu. So this is natural way to write this. And here again you have the same problem, right? So you have this constraint that xu belongs to 0 or 1. And what we can do is we can try to do this relaxing trick we said before, right? So this is not quite a linear program. The constraints are linear, that's good, and the objective is linear, that's good. But you have this additional constraint of xu is in 0, 1, which is not linear. Right? So you can make this linear. You could say 0 less than or equal to xi less than or equal to 1. And remove these constraints. So now the first question to ask is, suppose I look at this kind of a polytope for a graph. Okay, so I have a graph and I write these constraints and I look at this optimization problem. Right, so let's look at what I'll call the vertex cover polytope. So what are the constraints on this polytope? So this is something in n dimensions, right? So n was the number of vertices. And you have 0 less than or equal to xu less than or equal to 1. This was one constraint, and the other thing was for all edges uv bigger than equal to 1. And this is like you have n-dimensional space. Each of this is like it chops the space into parts, and then you want the overlap of this, right? So this is the picture we had. So for every edge you have a constraint, and you have also these bigger than or equal to 0 and less than or equal to 1 constraint. So your feasible set looks like this. Alright. And the objective. Okay. So now the question you could ask is, suppose I have a graph, okay, and I try to maximize this. So, I try to do this, minimize this, and suppose I try to satisfy all these constraints. So now the question is, could there be, could this feasible region have corner points that are non-integral? Okay, so that's one question you want to understand, right? So in this case, would you think that they have to be non-integral corner points?
They should all be integral. It's a cut across. It's the cut across the diagonals, right? It's a 0-1 space.
Mm-hmm.
And x1 plus x3 is a diagonal line connecting 1, 0, and 0, 1. And
Okay.
that's true for every pair of spaces. So
Okay.
all the corner points should be integral.
Well, not quite, right? So why would you? So that's true. I mean, it is true that so if you had this in 2 dimensions, what you said is right? But there is no edge between every pair of vertices. So you have this constraint only for vertices that have an edge, right? So you don't have a cleat for so
Last time there was a trivial counterexample we did last time, where we said everything's 1/2.
yeah, so that's another thing, right? So if you have if your graph was a triangle, all halves is actually a corner point. Okay, so equals xv equals x. So let's call it uvw. So this is actually a very good counterexample to what you said, because here you have all edges, but still this is a corner point. So why is this a corner point, by the way? So this is if my vertex has if my graph has only 3 vertices, then you are in 3-dimensional space, right? Because the number of dimensions is exactly the number of vertices in the graph.
You take any set of constraints, it will satisfy that. So it's at the intersection of
Not all of them, but yeah, it's at the intersection of these 3 constraints, right? xu plus xv less than or equal to 1, this plus this equal to 1, this plus this equal to 1, and this. So do you all agree that this is a point which is at the intersection of 3 different constraints, right? Which is basically xu plus xv equal to 1. This satisfies all these with equality, and this is the point at the intersection of these. And this is a feasible point, right? Because it satisfies all these constraints, and so that's why this is actually a corner point, because it is a corner and it is feasible. Okay? So you could have points that are the intersection of 3 constraints, but they are not feasible. So some other constraint could be violated. So that's why you could have points that are not corners like that. But in this case, actually this is a very good example. So in this case, I would encourage you to just literally draw all the hyperplanes and verify what all the corners are. Okay. So because it's just 3 dimensions, you can actually draw this. Okay. So yeah, I'm bad at drawing, that's why I'm not trying to draw this, because it will look very confusing. So, but you can even like plot these kind of things. So yeah, basically you'll have 3 spaces that look parallel to the axes, and yeah, so yeah, it's hard for me to describe it, but there will be a corner point at half, half, half. So, alright. Yeah, so this is an issue with this. Okay, so you could have corner points that are not integer, and this could be a problem. All right. But it turns out there's still a very simple way of okay. So I'm going to describe to you a simple way of rounding. And what was rounding? You start with any feasible solution that has any values. Okay, so it's feasible solution just has xi's in 0, 1, and it satisfies all these constraints. Right? And I'm going to describe to you a very simple rounding. We'll see why it's a good rounding. Okay? So the rounding is, take any variable with value xu bigger than or equal to half and set it to 1. Okay. And if xu is less than half, strictly less than half, set it to 0. Okay. So this is a very simple example of rounding. Okay, so it's you have a fractional solution, you want to make it into a 0, 1. This is probably a very trivial thing that you would guess, right? And I want to claim that if I do this process, the first claim is the 0, 1 solution you get is feasible. Okay, so why is this? So what does it mean to say it's feasible, right? So it means that the 0, 1 solution also satisfies all these inequalities. And it satisfies these inequalities for sure, because it's a 0, 1 solution, so clearly all the xu's will lie between 0 and 1. Okay. So what about these inequalities? Okay, so if I take any edge, if I take some edge uv, okay, and why is it that at least one of them will be set to 1? So stare at this procedure once more, right? So what we are doing is you had some fractional solution. The fractional solution satisfied these constraints. Right? So if you looked at some edge uv, so let's fix one edge.
Otherwise the constraint won't be satisfied.
Yeah, so this fractional solution xu xv, it satisfied xu plus xv bigger than or equal to 1.
So one of them had to be at least half.
Exactly. Okay, so does everyone see this point? So initially, before you rounded, at least one of them should have been at least half. Okay, because otherwise, there is no way xu plus xv could have been bigger than or equal to 1. Okay, and what that means is, after you round, at least one of them will actually be 1. Okay, the other could potentially be 0, but it doesn't matter. Or it could have happened that both were, this was half, this was 3/4, and both got rounded to 1. Okay, but that's still fine. Okay. So, yeah, think about this argument for a bit. If you have a question, let me know. But this is a very simple argument, okay, that look at any edge. Initially, xu plus xb had to be bigger than or equal to 1, like for in the fractional solution. So at least one of them should have gotten rounded up to 1. Yeah.
What about a case like bipartite matching where you have two variables added together and they're both 1/2, they both get rounded up to 1 and that would violate the constraint?
Yes, so this is true only for this vertex cover.
Okay.
Yeah, so that's why for those kind of matching problems you can't use that, so you have to use something else. Yeah, so this is why if you had independent set, you actually can't do this sort of thing. So independent set you would have xi plus xj smaller than or equal to 1. And there, if you did this, you would round both the halves. If you had two halves, you would round it up to 1. So that's the problem.
But if you rounded it in the opposite way, would it work for independent set?
No, it doesn't, because you mean if it was strictly less than or something?
So just change the, in independent set, if xu greater than or equal to half, set it to 0. And if xu less than half, set it to 1. Would that work for independent set?
No, right, because for a true independent set, you would have to, if it were a 0-1 solution to start with, then you make it an all zeros, then you flip it and then it's no longer an independent. Yeah, so. But anyway, so for vertex cover, it turns out that this maintains feasibility, right? And now, how is the objective changed in this process, right? So suppose the objective was, the objective value, sum over u xu, right? So how much could it change by doing this rounding? Is the question clear? So you're asking, you looked at the sum of xu for overall u, and you did this process. Okay, so you said everything that was at least half to 1.
At most
At most n over 2.
At most n over 2 is also fine, but this is actually at most twice the original value. Okay, so I want to claim that if the original value of sum over u xu was equal to k, equal to some parameter k, then in the end it is at most 2k. Okay, so after you do this process, it's at most 2k. So what would be a proof of this?
At most all x cubes are greater than or equal to half, then you're increasing the value by that much.
Yes, and if something was less than half,
Then you're reducing the value, it's
Yeah.
less than.
so is this argument clear? So what he's saying is, let's think of the original value as, let's say, xu. Okay, so this was the fractional solution. And let's set yu to be this rounded thing. Okay, so this is 1 if xu was bigger than or equal to half, and 0 otherwise. Then you have that yu is always smaller than or equal to 2xu, right? Because if xu was bigger than or equal to half, then yu is equal to 1. Okay, so which means by default yu was at most 2xu, and otherwise yu is actually less than xu. Okay, less than or equal to xu, so it's in particular less than or equal to 2xu, and that's why your new optimum, which is sum over yu is at most 2 times sum over ux. Okay. And equality occurs when everybody is exactly equal to half. So this is a very simple argument. Any questions about this? It's very simple, but it's pretty nice already, right? Because this gave you a 2-factor approximation. So what this says is, if you had an algorithm, so what this gives you is an algorithm that says if you had an independent set of size k in the graph, then this is an efficient algorithm that found an independent set of size 2k. Okay, so not interval, vertex cover of size at most 2k. Okay. The reason was you write your linear programming relaxation, and the value of this objective value of the linear programming relaxation will be at most 2k, because you could have put the optimal solution as a feasible solution, and then you do this rounding and you get at most a factor 2. So think about this for a little bit, but why this always gives you an optimal solution. So there's one small step here which I kind of just went over, but could go over it more slowly. So okay, yeah, let me create a new slide and go over it again, because I think that was a bit fast. Okay, so what I said was, so what is the algorithm that we now have, right? So the algorithm that we now have so this is the algorithm for vertex cover. So what you do is you solve the linear program. And do the rounding that we saw before. Okay, and return the solution that you want. Okay. Return the Y solution. So this is an algorithm for vertex cover, and I want to show that claim is that the objective value of this solution, of this Y solution, is smaller than or equal to 2 times the optimum. Remember, this is a minimization problem, right? So the lower your value is, the better. Okay, so the optimum is like the lowest value possible. Okay. What we are saying is the solution you output is not too much bigger than the optimum. And what I proved here is that the objective value is smaller than or equal to 2 times the smaller than or equal to 2 times the LP cost. Right? So by this I just mean 2 times sum over U x U. Okay, so this is what we showed before. Right? So I said that the cost of the number of vertices you output, which is the sum of the U by U, is at most 2 times sum over U x U. And this is what we saw by this clean argument. And now I'm just saying that, now I want to say that this LP cost is smaller than or equal to the optimum. Okay. So, is what I want to say clear? Okay. So I want to say that if I solve this LP, which is, the LP is just minimize sum over U x U of 0 less than or equal to x U less than or equal to 1, and for all edges UV xu plus xv bigger than or equal to 1. So if I solve this linear program and I compute the value of this, then this is smaller than or equal to the optimum value. So actually, what is the optimum? Just to make sure everybody is clear. So what do I mean by optimum here?
Smallest vertex.
Yeah, it's the value of the smallest vertex cover on this graph. Right? So you have the graph G, and optimum is value of the smallest vertex, or number of vertices in the smallest vertex. The question I'm asking is, why is the solution to this linear program, why does it have an objective value that's smaller than or equal to the optimum? So note that if I prove this, I'm done, right? Because I showed that whatever value I got is at most twice the optimum solution for the linear program. And if I can show this is at most that, then I have proved that this is less than or equal to 2 times the optimum. Okay, so is this clear? These 2 steps.
It's lesser if you have a vertex with non-integral points.
And why is that? So first, actually, is this statement clear? Is what you have to show somewhat clear for everyone? Basically, what you're saying is, you have this true optimum, which is the size of the smallest vertex cover, and you wrote down this linear program, you solved it, you want to say that the optimum objective value is smaller than or equal to that.
That sum up in the top right, is that summing the weight of the edges?
No, it's sum over vertices. Sum over vertices u of xu. Right? So vertex cover is a problem where you have to pick vertices, right?
Right.
And xu is supposed to be 1 if you pick the vertex and 0 otherwise. And that's the ideal solution.
Okay.
But we can't enforce xu to be either just 0 or 1. All you can enforce is xu is between 0 and 1. And it could take values in the middle. And you have these other linear constraints. Yeah.
So we're dealing with 2 versions of the same problem. One just has more constraints than the other.
Exactly. So this is a great way of putting it. So what he's saying is, the optimum solution, okay, so also satisfies all these constraints, right? And furthermore, the optimum is a 0-1 solution. So it's either 0 or 1. xu is either 0 or 1. So in particular, if you took the optimum solution, okay, so S, let's say, is your optimal set, optimal vertex cover, okay, and it has size equal to opt, and you plug it in, okay, so in the sense that you put xu equals 1 if u is in S and 0 otherwise, then that is a feasible solution for the linear program, right? So you don't know what the optimal solution is, but you know that it is a feasible solution to that linear program. Okay. So in particular, the best solution to the linear program will have to have an objective value that's smaller than or equal to the objective value for this solution. And that's why you have that the LP cost is smaller than or equal to the optimum. Okay, because it's a minimization linear program, right? So that's the reasoning here. So I'd say, yeah, you should think about this. So this is a very powerful notion that's commonly used in approximation. Okay, so you should think of it as your true solution is one feasible solution to the linear program, and the linear program could have a different optimum. But what you know is that optimum value is smaller than or equal to the value of the true of this solution. So and what you're actually getting is a solution whose cost is at most 2 times this. So that's why you are no worse than 2 times optimum. Yeah. So think about this, and we'll see another example next time, and we'll.
So the linear program would give you a solution which is not the optimum solution. but when you round it off,
Yeah.
so when you round it off, it's 100. So that objective value of y, shouldn't it also be lower bounded by sorry, the objective value of y, is it also